Our philosopher, Socrates, begins his day like any modern man, with a chilled iced coffee. Occupied by the mysteries of life, Socrates later returns to his coffee to find a cup of melted ice.
Archimedes, I was drinking my coffee. Where's my ice?
Let's talk thermodynamics.
The reason your ice melted is explained by the second law of thermodynamics, but before we get there, let's start from the beginning. Energy is defined as the ability to do work. An example of energy is thermal energy, which is the energy within an object due to the movement of particles. There are lots of different types of energy, such as chemical, electrical, kinetic, and many more. Now, in order to understand the second law of thermodynamics, first we have to know the first law. The first law of thermodynamics states that the energy can only be transferred between types of energy. It can never be created nor destroyed. Heat is thermal energy, transferred between systems due to a temperature difference. The second law of thermodynamics outlines the tendency of this heat transfer. The law states that the entropy of an isolated system will always increase over time. Entropy is a measure of how spread out thermal energy is, with the equation delta S equals delta Q over T. This can be thought of as the level of disorder or randomness in a system. As such, an isolated system will become more disordered over time. Think of it like the tendency for dominoes to fall over, a Jenga tower to collapse, or water to disperse when released from a glass. But why do systems tend to higher entropy, you may ask? It is all due to probability. Think of it this way: if I have 2 dice on a given number and I drop it, there's a small chance that both will again land on the same number. However, if I have 6 dice, the probability that they will all land on the same number is lower. Now imagine if we had 6 billion, the number of molecules in a glass of water. The probability that they will spontaneously arrange themselves in an ordered position is so improbable that it is never observed. Now looking at our glass of water, the molecules within the ice cube are ordered molecules that are vibrating slowly with less thermal energy and therefore low entropy. The coffee fluid has a faster moving disordered molecules with higher entropy. Just like with the dice, it is much more likely that the thermal energy will be transferred from the fluid to the ice. When this occurs, the ice melts into a liquid and there is an overall increase in entropy of the system. What if I showed you this? That looks weird, right? Systems must have a gradual progression from lower entropy to higher entropy. The second law of thermodynamics outlines this natural order of events and the arrow of time, from your delicious iced coffee to, well, not so iced coffee. And that, Socrates, is the story of your iced coffee. It's all just a grand dance of energy and entropy unfolding in a one-way journey with the arrow of time.